All right. So, I talked about what is a photon, and I mentioned these are the details about the photons. The things that you need to worry about is the wavelength. That is the most important thing for a photon. So, in the wavelength, we will decide how much energy each photon has. H mu is c by lambda. C is the speed of light, lambda is the wavelength. So, and the rest of it is not that important. And so, the light that comes out as a photon, each photon is an independent unit. So, each photon will interact with a molecule. Now, we need to understand what exactly we mean as a molecule. So, I will tell you a little bit about a molecule, which you probably know already. Okay, we don't need all this, we go to this. So, the molecule, as we know today, is different from what it was considered to be 2,500 years ago. So, in those days, they thought a molecule is made up of small units, and those units today we call them as atoms, and the atoms consist of smaller things. So, when we think of a molecule is a connection of various atoms. So, each atom is standing at a different place in a molecule, and each atom is different. The inside of each atom, it contains electrons and protons and nuclei and the neutrons. So, when you think of an atom, that atom is basically it consists of electrons, protons and neutrons. And this atom and that atom, these three atoms if they are connected, we call them as a molecule. So, when a photon comes and interacts with a molecule, it is going to interact with these various, the molecule as a whole, but at the end of all this stuff, it will be interacting only with an electron. The electron, it has only enough energy to interact with the electrons and move it from one orbital to a different orbital. Okay? So, this is the way we think of things today. So, a molecule, a matter or something or a material is made up of a large number of molecules, and each molecule is made up of number of atoms, and each atom is made up of a lot of electrons. When you think of a molecule, you think of them as a collection of electrons. Okay? And then so, the fundamental components of the molecule is basically electrons. Now, the photon that comes and interacts with the molecule, it is going to interact with the electrons. So, we need to know where the electrons are and how they are distributed in a molecule. That is not that easy. That is much harder than just saying electrons, but it is where it is in a molecule is not, we don't know. Okay? So, we guess these things. Okay, you might have taken a course in physical chemistry, something like quantum chemistry, which talks about Schrodinger equation. Does it Schrodinger, does the guy sound any bell? Are you familiar with the Schrodinger? Okay. So, whether it is a simple molecule like this CH4, or whether it is a complicated molecule like this, or even more complex molecule like this, like a protein. Okay, simple methane or a huge molecule like a protein, it is basically a collection of electrons. And the only question is where these electrons are in a simple molecule like CH4 or a big molecule like this proteins or some complex, ruthenium complex or whatever. We don't know exactly where the electrons are. So, what we do is we use this equation. This equation is called as Schrodinger's equation. This is not that very intuitive. It is a little bit complex maths, but we don't have to know all those things. But because we can try to have a picture in our head more than the equations. Okay? When you think of a molecule, there are going to be nuclei, and the nuclei are surrounded by electrons, and these nuclei positions and these positions of various atoms are different. So when you say psi, it defines everything. So when I say somebody's name, other person can immediately recognize how the person looks like. Okay. So if I have a psi for you, psi for her, psi for somebody else, and psi is basically your name. So if I tell so and so I met so and so in Shanghai or in Chengdu, I don't have to tell the details, how tall he is, how fat he is, or what color he is. All these things I don't have to tell, because as from the name you can immediately guess, immediately know who he is. Okay. So like that, psi, if I say the psi for CH4, if you are really a good mathematician, they will immediately know what I'm talking about. If I say some other psi with this, all this, then he knows if I'm talking about a protein. I don't have to tell the guy all these details. So a molecule is basically defined by this psi. And then that psi contains information about the positions of atoms, positions of electrons, and the spin of electrons. Everything about the atom or a molecule is contains in this psi. Okay. If you know that psi, you can calculate the energy. Okay. That energy is coming from here. This is the energy, and this is the operator. This is called the operator. Okay. So this is a standard equation. H psi, E psi is a standard. And if you want to know the more details, you will have to take a course on quantum chemistry, which will be a little bit more tedious. Okay. So the psi defines all this, and the psi, to make things simple, because our goal is to make things simple, because it is not that easy to figure out a psi for something, because the psi contains everything, atoms, the nuclei, electrons, the spin, all the information are contained in this tiny psi. Okay. So if you want to understand, you separate each one separately. For example, the psi you can split into smaller pieces. This psi 0, it talks only about electronic configurations, and this psi, it talks about the nuclear positions in a molecule, and this one talks about spin. So when you think of a molecule, it contains positions of nuclei and the electrons in the around the nuclei, and electrons have spin. This is alpha or beta. That is what is, the electrons can rotate around it this way or the other way. You don't know how it is rotating, so they can have spin. So if this one, it tells all three, but all three are interconnected. If you move the nuclei, electrons will move. If the electrons move, the spin will change. So you cannot really calculate this by any means. Even today, you cannot calculate the psi for even a simple molecule. Okay, only for the hydrogen atom, it has been calculated. Beyond that, it is just you will have to do a lot of approximations. The important thing for you to know is when we say psi, it represents electronics, nuclear, and the spin. Okay. So for example, if I have a molecule connected A and B, so this A and B, I know the distance between the two, and then once I know the A and B, I know where the electrons are. So now, if you know that one, if you move the nuclei a little bit away, the electrons will change. So now you don't know where the electrons are. So what is going to happen is the molecule is always vibrating, so the positions of electrons are always changing, and since it is changing, at no stage you know exactly where it is. Okay. So, but we cannot give up. If you just give up, I don't know this where the electrons are, then then you are not going to make any progress. The best thing is make assumption. Okay. We assume that the two nuclei are fixed. They are not changing their positions. If they are not changing their positions, then you can tell the electronic configurations. That is not the correct, but there is no other solution. Okay? So that's how we define a molecule. When we say where the electrons are in a molecule, it is based on the assumption that the molecule is not moving, it is stationary. So the atoms in a molecule are not vibrating. So if you want to know the positions of electrons, you fix the nuclei, you calculate, and then go to another positions, fix the nuclei and calculate. So you keep on calculating hundreds and hundreds of these, and then you can connect these things. So that is how it is done. Okay. So this psi consists of this and this. You will see pretty soon, if you move this, this will change. If this and that couples, then things will change. Okay. Okay. So there are two people, Born and Oppenheimer, because before this approximation was made, it was impossible to understand how a molecule looks like. What is the electronic configuration of a molecule? It is not easy to know. Okay. That was not long ago. This is about 50 years ago. Okay. So he was his teacher and Oppenheimer was his student, and he worked for him. They decided, okay, we will make an approximation that is called as Born-Oppenheimer approximation. This is a very important approximation. It is an approximation, but we know when we say something, when we say, okay, electrons are in the next building, we are assuming it could also be there in the other building. So we don't know exactly where it is. It is in between the two buildings, it is there. So we can, at no stage we can say for sure whether it is here or there. So we just approximate things. Okay. See, what we do, you see, the reason for this is when you move the nuclei, the electrons will move. Then what happens is how fast the electrons move and how fast the nuclei move, they are very different time scales. The motions of nuclei are very, very heavy. It contains a lot of protons and the neutrons and all this stuff. So it will move very slowly. The electrons are like a bee. So they can move very fast. If this nuclei moves, that will move very quickly. On the other hand, if the electron moves, the nuclei will not be able to move that fast. So when the electrons are going from one orbital to a different orbital, the nuclei position will not change. It will remain at the same place, but after some time it will move. So it takes a while. Okay. So this is the approximation they make. Electronic motions are faster than nuclear motions. So, and also the same thing for other things here. So what you do is, to understand a molecule, you separate all three. So the nuclear positions, see, in a molecule everything is moving all the time. But now we fix it. We say, okay, the positions of nuclei is fixed, then I can understand a little bit about electronics. But that is not true, but that is, we just have to fix this one, and that one will automatically come. Similarly, the spin. Okay, this is a very important thing that you have to remember. This is what is called as Born-Oppenheimer approximation. Have you ever heard of this before? Born-Oppenheimer. Have you ever heard of this guy called Born and Oppenheimer? No? Okay. Oppenheimer is a guy who made the atom bomb that was dropped in Japan. He was in charge of the program to make the bomb. That was about, I don't know, 70 years ago, 1940s, 45 or 46. They destroyed the city of Osaka, Tokyo, all the places where they just bombed. America bombed no, it is Nagasaki and Hiroshima. These were the two places they dropped the bomb, and he was the person in charge of making the atom bomb. First time in the world, they were the people, and he's an outstanding physicist. He is a nuclear physicist. So he was responsible for this approximation, which we use today. Okay. So to know the electrons, you have to know what exactly electron is. Electron is like a photon. It is also not that obvious what it is. although we think we know everything about electrons, electrons also acts like a wave, it also acts like a particle. Photons, we already said, it is like a particle. When it hits when the photon hits something, it can behave like a particle or it can behave like a wave. Electrons also can be like a wave, it also can be like a particle. So when the photon comes and hits the electrons, both can act like a wave or both can act like a particle depending upon where the electrons are there in the things. Tell me, electrons, you must have studied electrons many times in your schools. Is it negatively charged or positively charged or no charge? Does it have a zero charge, plus charge or minus charge? This is a test for myself, how much you know. Okay? So it is negatively charged. Okay? And then the most important thing about, which is not very obvious, electrons have spin. Okay? So that is the most important thing that is going to be coming up in the photochemistry course. So electrons have a spin of half. Okay, that is whatever that h bar, and since it has a charge and then it is moving, it will also have a magnetic field. So electrons are charged, and then when something is charged and moves, it will create a magnetic field. When it goes around, then you will have a magnetic moment. Okay. So it is very small. The size is about 0. Whatever the size is, extremely small, and the electrons are the ones which are holding the two atoms together. Okay. So if you have an atom here and another atom here, these two atoms are covered with electrons. They are negatively charged. This is negatively charged. This is negatively charged. And when they come closer, there is going to be repulsion. So in principle, you don't think any atoms can come very close because both are negatively charged. But then we know for sure two atoms, when they come close, there is an attraction. That attraction is what is holding the molecule. A molecule is made up of a whole bunch of atoms, and these atoms are held together by the electrons. Although they are negatively charged, that negative charge is the one keeping the two atoms close to each other. This is what you might have studied in Lewis octet rule. You must have studied two pairs of electrons are holding the two things together. Because what happens is when you have two electrons, that electron can be attracted by this nuclei, which is positively charged. That electron can be attracted by that nuclei that is also positively charged. Then what happens is these electrons can neither go here, can neither go there. They're just like a glue. They hold the two pieces together. Okay. So automatically changed. Okay. So this is what happens is the electronic motion and nuclear motion can be separated. That is the main contributions of this Born-Oppenheimer. Because when you move the electrons, it is, as I already mentioned it to you, it is extremely fast, 10 power minus 15 or minus 16 seconds. Okay, when you move the nuclei, it takes 10 power minus 12 seconds. So if something is moving at 10 power minus 15 seconds from there to here, this is nuclei which is sitting here, it cannot move in the same speed. So it will move after it has gone over here, it will move here. So there is going to be a separation between how fast the nuclei and the electrons move. That is what is this. So since they move at a different speed, you can fix the nuclei and then get the structure of the molecule, and then change the nuclei, get the structure of the electrons. So we focus on these things. So in terms of where the electrons are in an atom, this is a known thing, because at the end of it, you need to know where the electrons are in a molecule. Because we are not dealing with atoms. We are not talking about atoms like hydrogens or xenon or sodium or something. We are talking about benzene or anthracene, some big molecules. Molecules contains a lot of atoms. Okay? So you cannot start from some confusion and then solve the things. You start from something you know and then slowly build it up. So we know for sure from the works of Niels Bohr, the electrons in an atom are in various orbitals like s, p, d and all these are known. Okay. So, if I have CH4 carbon, 4 hydrogens, I know where the electrons are in the hydrogen atom, where the electrons are in the carbon atom, but they are all now close to each other. Now, the question is where the electrons are. So, the electrons, so we start from here, we call them atomic orbitals. From the atomic orbitals, and then we visualize, now there are a whole bunch of electrons in this molecule all over the place. Now, these electrons are seeing 1 carbon and 4 hydrogens. That carbon, each one is charged. Because it is charged, these electrons are not going to be localized around hydrogen or around the carbon. So, it is going to be all over the molecule. So, that is called as molecular orbitals. So, to get to the molecular orbitals, you have to know the atomic orbitals. And then we take the atomic orbitals and mix these things up and generate a molecular orbital. So, when the light comes and looks at the molecule, it is not going and looking at atomic orbitals. It is looking at the molecular orbitals. From the molecular orbitals, it goes from one place to a different place. That is what we want to talk about. Okay. Okay. Now, we are talking real sort of real molecules. So, for example, you know this molecule what it is? This is a simple molecule. Okay. This is not a very complex organic chemistry. This is it acetone, or is it formaldehyde, or is it benzene? Tell me one of these three. It is only one of those three. Is it a formaldehyde, acetone, or benzene? Okay, this will give me some impression how good you are in organic chemistry. Or this is not a big organic chemistry. This is a kindergarten organic chemistry. Okay, is it which one is this molecule? Aldehyde. This is a formaldehyde. Okay. So, formaldehyde, if you look at this contains a carbon, a hydrogen, and an oxygen. So, hydrogen has got one electron, carbon has got some number of electrons, oxygen has got number of electrons. So, this molecule is the carbon and the hydrogen bond, this bond. There are 2 electrons here, 2 electrons here, 4 electrons here. So, this is what is holding this molecule. So, if you just leave them apart, this hydrogen will stay away with 1 electron, this hydrogen will stay with its own electron, carbon with its own electron, and oxygen with its own electron. But when they come very close to each other, then they stay together as it is, and then they do not go away. Once they come together, then it forms a molecule. So, now we want to know where the electrons are, because when the light hits this molecule, it is the interaction only between the electron and the light. It is not this carbon nuclei that is interacting with the light. It is the electrons are interacting, because electrons are a wave and the light is a wave, they can interact. Now, we need to know where the electrons are in this molecule. Where the electrons are, we know where the electrons are in hydrogen, where the electrons are in the carbon and in the oxygen. We know independently, we know where it is, but we do not know as a whole molecule, we do not know where the electrons are. So, what we do is we go back and it is not that straightforward. These things can become a very complex problem, but if you do not want to make it too complex, then we cannot solve the other things. So, we take some simple things we know and build the picture. Okay. Now, there are lots of electrons in this molecule. Okay. There are going to be electrons in the hydrogens, that is in the 1s orbital. There are electrons in the carbon, and then there are electrons in the oxygen. So, the way the molecule structure is written, we say for example, there are some electrons inside of each one, carbon 12, oxygen has got 16. Of these 16 electrons, most of them are not that much important, because those electrons are inside this, deeper inside, they are not disturbed by this carbon. Only the outer electrons, those are the ones which are going to be affected by when you bring something closer to that thing. So, for example, if I have this is let us say this is like oxygen, it contains a lot of electrons in various orbitals, 1s, 2s, 2p, 3s, like that. Okay. So there are some electrons far away from the nuclei, there are some electrons closer to the nuclei. So if you have the electrons which are far away, if something comes closer, those electrons will be affected, and the ones that are closer to the nuclei are not going to be affected by the one that comes closer. So we call them as inner orbitals, and the bonding orbitals, that is the one that is bonding these two, and the frontier orbital, that the frontier is the one way outside. So you can think of a number of electrons in the molecule as a whole bunch of electrons out at the outer shell, something inside, something very close to the nuclei. Very close to the nuclei are held by the nuclei plus and minus charge, they attract. The one that are outside, the attraction is sort of much less, and these are the orbitals that are important. And these orbitals are not important for us now. Okay? They are important, but for our purpose that is not that important. Okay? So if you take this molecule here, okay, so all these things in the atomic orbitals are deep inside, so that is not important. The last, some of these orbitals here, they are far away from these nuclei. Those are the ones that will get disturbed when the light hits this molecule. The electrons that are over here, these electrons are closer to the carbon or closer to the oxygen, hydrogen, that is deeper inside these things, they will not be affected. But what is getting affected is outer shells. The outer shells are the pi orbitals, the n orbital, that is this oxygen has this, look at this carbon oxygen. This carbon oxygen bond is double bond. Double bond means there is a carbon oxygen single bond, which is sigma bond, carbon oxygen pi bond, which is the double bond. So there is one bond, two bond, so single and double. So when there are 4 electrons connecting carbon and oxygen, only 2 electrons will go per one bond, because they cannot have more than 2 electrons in an orbital. Okay? So this one is, this will have carbon oxygen pi bond, and then this oxygen also has what is called as non-bonding orbitals. Those are not involved in bonding between carbon and the oxygen, but they are outer shell. So if you have this molecule, there are some electrons outside, those are the ones which are non-bonding orbitals. The most important orbitals for our purpose is only this non-bonding orbital and the pi orbital. So we will focus only on those. We will not worry about the rest of the electrons, because when the light comes, it is only seeing what is easy target. Whatever is inside, it cannot go and interact with that, because first we have to solve the outer shell, and those electrons are going to be important. Okay, so here, so this 1, 2, 3. Okay. Now these are real. You just have to figure out how does this work. So we talked about this. This is the same compound. So it contains a lot of electrons here. From here, all the way from here to here, the electrons are not that much important. They are tied very closely to the nuclei. The ones that are weakly held are this pi orbital and the n orbital. And each orbital will contain 2 electrons. You cannot put more than 2 electrons. So when you draw a line like this, that represents a molecular orbital or an orbital. Okay? And there are 2 electrons here and 2 electrons here. Okay, when you have a pi orbital, these are all made from molecular orbitals. We don't have time to go through the details of all this stuff. When you make a pi orbital, you will also make a pi star. When you mix 2 orbitals, 2 atomic orbitals, you will get 2 molecular orbitals. One will be a bonding, another will be anti-bonding. Okay? So when we have a pi orbital here, that means it is holding this carbon and the oxygen. That is the electrons are not localized on the oxygen or on the carbon. It is delocalized between the carbon and the oxygen. The electrons are not completely on carbon or on oxygen, but it's somewhere in between here. And when you to make that orbital, we mix the atomic orbital of carbon and the oxygen, we make a pi and pi star. Okay? Pi will always be lower, pi star will be higher, and now if you put the electrons, the 2 electrons will go in pi, and this orbital will be empty. And then there are electrons on the oxygen, which is not interacting with the carbon, but they are a little bit away from the oxygen nuclei, so they are called non-bonding orbitals. So that is these two. Okay? So the electronic configuration for formaldehyde, very simple in terms of molecule, is pi and n. So these are the electrons. So this, when you draw these things, you don't draw like this. You draw like this because they represent the energy. Whatever is lower one, that is more stable. Whatever is higher one, that is less stable. Okay? So this is the less stable, more stable, and the most stable one. If you have 4 electrons, first 2 goes into the most stable, the next 2 goes into this one, and this one is left empty. Okay? So the electronic configuration we visualize for this molecule is going to have 2 electrons between the carbon and the oxygen, 2 electrons on the oxygen, which is less energetic, which is less held by the oxygen. So when the light comes, those electrons are the ones which is going to be interacting with this and with that. Now the question is, what happens when the light interacts with this molecule? Okay? Now this is called as electronic configuration. So, when you say there are various configurations for the molecule, nuclear configuration, that means a distance between A and B, B and C, that is the nuclear configuration. This is the electronic configuration, where the electrons are in a molecule. This tells you between A, B and C, there are electrons are here, next one is here, third one is localized only somewhere else. Okay? So this is what is called as, this is the ground state electronic configuration. When you have this compound in your hand, the electrons are going to be distributed like this. But there is a possibility you can have 1 electron here and 1 electron here. That is not the most stable arrangement. That is less stable arrangement. That is called as, for example, here we call them as pi n and pi star. So you keep track of where the electrons are. The electrons in this one, there are 2 electrons in the pi orbital. There is 1 electron in the n orbital, 1 electron in the pi star orbital. So if you want to tell somebody, then you will say n to pi star. I have formaldehyde n to pi star in my pocket. Okay? That means the electrons are going to be 2 electrons on the pi, 1 electron on the n, 1 electron in the pi star. That is one electronic configuration. And there is also possible you can have 1 electron here and 1 electron here. You take the 2 electrons from this, on one of them you put it here. That means there is only 1 electron in the pi, 2 electron in the n, and 1 electron in the pi star. So this one and that one, they are not of the same energy. Okay? The energy depends upon where the electrons are. This is the most stable orbital. Next stable orbital, all the 4 electrons are the first 2. And you cannot put the 2 here, because each orbital can have only 2 electrons. And then, so there is the n to pi star. This is less stable than this, and this one is even less stable than this one. So every molecule will have several different electronic configurations. So it can have configuration 1, configuration 2, configuration 3, configuration 4, 5, like that, where the electrons depending on the orbitals. But the most stable arrangement would be the filled orbitals, like this one, where the lowest orbitals are completely filled. So when you take a molecule, when you buy a molecule from some chemical company, then the electrons are going to be in the ground state. But these are called as excited state, because electrons have been moved from this this one to that one, or from here to there. So these are called excited states. These are not the most stable arrangement, but you can make those arrangements. You can make the molecule to go into that configuration if you give enough energy to the molecule. But you cannot give in terms of heat, because the electrons to go from one orbital to another orbital, it needs a different type of mechanisms, not like just heating it. Like heating means vibration will get further and further. If the electron has to go from one here to there, then it is just heating is not enough. That's where the light comes in. So this is we talk about, when you say HOMO, that is the highest molecular orbitals. So the orbitals is, the electrons are in an orbital. We know in an atom, they are in an atomic orbital that is going around a single atom. In a molecule, the electrons are going around a number of atoms. That's why we call them as molecular orbitals. So the molecular orbitals are going to be 1, 2, 3, 4, 5 like that. Okay, so if you have like 6 of those things, the orbitals are 1, 2, and 3. The third one is the highest occupied molecular orbital. That is the highest one. And the next one is empty. So the next one, there are not enough electrons to fill all the orbitals. So since we cannot fill all the orbitals, up to a point we fill whatever is the highest one that we fill, that will be called as highest molecular orbitals. And the next one is called as lowest unoccupied molecule. Okay. So if you have, for example, so one multiplication like this. These are all the molecular orbitals. Suppose you have 6 electrons in the molecule. What will happen is 2 will go here, 2 will go here, 2 will go here. And then there are 3 more orbitals, but these are empty. And these ones are fused. In principle, the electrons that is here, it could be here or here or here, in principle. If it is here or here or here, they are called excited states. So this one is called as highest occupied molecular orbital. Each one is a molecular orbital, and this one is highest occupied, and this one is lowest unoccupied molecular orbital. So to go from here to here, this is the energy gap. That energy gap is small. If you want to take an electron from here to here, that is going to be more. So that will be different state. So this is what happens. So when you take a HOMO and then move to the LOMO, the light, but if you go from here to here, it needs the interaction with the photon. So if you just by heating it, it will not happen. That's why the photochemistry you need more. Okay. Here. So for example, if the electron is going to go from here to here, so as you see already, there is a gap. Here it is more stable. If you put the electron in this place, it is less stable. So that means to take an electron from here to here, you have to put energy corresponding to that gap. That gap is what we call, if you remember, we said h mu. So if it is like a 50 kilocalories, you have to calculate what is the mu you need for that. So that kind of light that you have to use. Okay. So here, R is something in the ground state. When you put a star on top of it, that means it is not in the ground state. The electrons are in an orbital, which is not the most stable one. It is the less stable one. That's where the electrons are. So the gap between R and R star is the energy difference between E2 and E1. Eventually, that is going to be h mu. The mu is c by lambda, and we need to know this lambda. So, if you want to take a molecule, if you want to take an electron from here to here, you need to provide this much of energy. If you want to take from here to here, then you have to provide this much of energy. So the wavelength will change depending upon how much is the gap between the various states. The lowest one is called S0. second one is called as S1, third one is S2, S3, S4. Okay. The energy difference between S0 to S1 will change from compound to compound. It is not a fixed number because the electrons in benzene is in one orbital. If we take naphthalene, it is a different orbital. If we take anthracene or pyrene, it is going to be different. So the gap between S0 to S1 will change from one place to another place. So for example, in the case of benzene, the gap is 110 kilocalories. That is, if you want to go from here to here, in benzene, this gap is 110. One more gap. If you take naphthalene, the gap is 90. So when you put a picture like this, it doesn't mean it is always fixed. This one is going to be a different number because we have a different molecule. And you take anthracene, it is 70. Okay. So you have to know what is the gap between S0 to S1 for each compound. That is, you can get it from absorption spectrum. It is not that difficult. I'm pretty sure many of you who do some fluorescence, you know how to do this stuff. So the most important thing is, you notice this the gap is varies with the compound. The other thing is, I will tell you a little bit later about in detail. Every molecule will have singlet and the triplet states. Because now here you have two electrons. These two electrons have opposite spin. But if you put one electron here and one electron here, they can have the same spin or opposite spin. If they have the opposite spin, it is called a singlet state. If they have the same spin, it is called the triplet state. Generally, the triplet states are lower in energy compared to the singlet state. I will tell you why, it will be later, but it is common. You can see the electronic configurations are exactly the same, whereas the spin configurations are not the same. Because the two electrons, there is one electron in this place, other electron here, but then they have these two, they have different spin, that means it is singlet. If these two have the same spin, it is called as triplet. And the energy of these two electrons, if the spin are the same or different, are not the same. Okay, that's what you see here. Benzene, the triplet state is 80, naphthalene is 75, anthracene is 60, so it varies from one. Always you see here, it is lower than. Okay. Now, so if you want to take a molecule from R to R star, the way we do it is shining light. The difference between R and R star is that these two does not have the same electronic configuration. They have the same number of electrons, everything else is the same, excepting where the electrons are not the same. In this case, it is all the filled orbitals. In this case, the two electrons are separated by orbitals here. So here R corresponds to this, R star corresponds to that. Okay. So the two electrons are in two different orbitals, that would be called as excited states. When the two electrons are in two different orbitals, they always want to come back. They are not going to stay here. Okay. So this excited state, that is this one, where the electrons are, we separated these two with the help of light. The light that the molecule absorbed, that was used to separate the electrons. Now the light is gone. Now the molecule has got all the electrons with energy with it, but it is not very stable, so it wants to come back. So if these electrons will always come back here. When it comes back, if it comes back the same structure, that is the molecule, that is called as photophysical. That means it will emit light. It will give back the light and come back down. That's what many of you study as fluorescence. When you study fluorescence spectrum, phosphorescence spectrum, and all these things, it tells you molecule went up, the electrons went to a different orbital, and then it came back down. How fast it comes, it depends upon number of different things. Other possibility is when it goes to the excited state, the molecule, because now we have separated the electrons, they have more energy, so the positions of nuclei can change, and if it does change, that is a chemical reaction. That means you don't have the same starting structure. So if the molecule is here, the electrons were here, now one electron is here, another electron is here. This electron is away from the nucleus, so that electronic configuration of this particular nuclear structure is not the most stable now. So the nucleus will change its positions. If it sufficiently changes, then what happens is there is a new molecule. It looks like a new molecule. When it looks like a new molecule, that is a reaction. That means reactor went to a product. Okay. So when you excite a molecule with a light, it will go to the excited state, and then it will come back the same way, emitting light. It will be called physical. If it uses to move the nuclei, it is called as chemical. So it can be either it can be photophysics or it can be photochemistry. Okay, we will stop here for a second and let's see whether you have any questions. Okay, questions? No questions? No? So you will all get A in the test on Monday. Next on Monday test, everybody gets A. So we don't have to take a test. Okay? Alright. Here. You know, in photochemistry, one of the most important things is addition to wavelength of light that you use to excite. The time is very important. If you are doing a synthesis thermal chemistry, it doesn't matter. The reactions always take longer time. So you can leave the things and go away somewhere and come back. Okay. If you are doing photochemistry, you cannot go away and come back. If you are going to record a fluorescence spectrum, you should stay there. You cannot wait for this. You go to some place, have lunch, and come back, and then the continuation. It doesn't happen. Okay. So the time scales are, for example, it can be 10 to the minus 15 seconds. 10 to the minus 15 is exceptionally fast. Okay. So, for example, normal thing is a few seconds, and then it can be milliseconds, 10 to the minus 3, and then microseconds is 10 to the minus 6, nanoseconds, 10 to the minus 9, minus 12, minus 15. So the time scales are very important. For electrons to move from one orbital to another orbital, it takes only 10 to the minus 15 seconds. For the nuclei to change their positions from A to B, it takes about 10 to the minus 4 seconds. For spin to change for the electrons from one spin to another spin, it will take around 10 to the minus 6 seconds. So these time scales are very critical. So if you have a molecule in the excited state and then it wants to come down, fluorescence, most of the time it will happen in 10 to the minus 9 seconds, nanoseconds. Nanosecond is 10 to the minus 9. You don't even have time to go out from this, open the door. It is much faster than that. Okay? So these time scales, you know, to study this kind of chemistry, you know, people use time resolved spectroscopy. That means you take a spectrum now, and after about 10 to the minus 6 seconds, you take another spectrum. So it is not that easy to take a spectrum with your hand. Because 10 to the minus, if you move your hand from here to there, it takes, you know, maybe a millisecond or even longer. Okay. So for this kind of things, you know, I showed yesterday this is the same thing. So we use, for example, flash photolysis. That means you have to turn on the switch. Turning on the switch itself, it takes a few seconds or maybe half a second. So if you, by the time you turn on the switch, molecule will already come down. You know, so what you have to do is you have to use some techniques, and these people they invented those techniques, which is Narish Porter. Narish was his boss, and Porter was his student, and they got the Nobel Prize for this in 1967. And the more famous person is Ahmad Zuhail. He is from Egypt, and he did his PhD and postdoc, and he was a faculty in California, Caltech, California Institute of Technology, and he got the Nobel Prize in 1999. Okay? So the time scale is also very critical. The wavelength of light is very critical, and you also should know the electronic configuration of the molecule. All these three things are very important. Okay? Now, okay, so how do I know each molecule will have different things? If I take naphthalene, the energy gap is something, and how long it lives there is different, another thing. If I go to the benzene, the gap is larger, and how long it is going to live there is different. So you have to keep track of all this stuff. So one way to keep track of all this is by a picture like this. This is called as Jablonski diagram. When you go and look at your book, I think I saw she has the Chinese version of the book. Maybe you can show it to them. I don't know whether they have seen it. I don't know. You can just get up and then show everybody, So if you want to buy the book or borrow the book, that is useful. So the way we do it is, this is the ground state, and this is the excited state. In the excited state, when you write 1, that means that is the first excited state. And then when you put S, that means the configuration is singlet. When I say singlet, tell me the 2 electrons have the same spin or opposite spin? Opposite spin. So the singlet means the 2 electrons are, one is alpha, another one is beta. They cancel each other. At the end, it is a 0 spin. That's why it is called singlet. And then when you write T, this singlet state will always have a corresponding triplet state, because the electrons can have spin like this, or they can have the same spin. That will be triplet. The triplet, as I mentioned to you before, it is always going to be lower in energy. So if you take a molecule, you put S1 and T1, and if you have a scale on this side, I can tell you whether you are looking at the So this is a very generic picture. You don't know what it is, what kind of molecule it is. If you have the number on the side, then you can tell whether it's naphthalene or benzene or anthracene and all this stuff. That's how people keep track of all this. So this energy of this state, energy of that state, and then also how long it lives, it is controlled by how fast they come down. Faster it comes down, the lifetime will be, okay, tell me, if it comes faster, the lifetime will be short or long? Lifetime, it tells you how long the molecule lives here. How long it lives there, it is controlled by how fast it can come down. How fast it comes down, it depends upon certain rules we will talk about. How fast it is fluorescence and then radiationless, all these things will make the molecule come faster. Faster it comes down, will the lifetime will be short or will be long? This is a very intuitive question. It is a very general knowledge. Okay, shorter or longer? Okay, till you answer the question, I am not going to move, I will not. Okay. Faster it comes, the lifetime will be short or long? If you don't understand the question, raise your hand. If you don't want to answer the question, that's a different story. Is it short or long? If a molecule goes there, if it comes faster, will it live there longer time or shorter time? Okay, no, let's see whether anybody else has got something to say. Molecule gives there. We put the molecule from here to there, and from there it wants to come down. It has a way of coming down faster. If it comes faster, will it live there shorter time or longer time? That is the question. Okay, what's the question? What is the answer? This is not that difficult, okay? It is, you don't need to know chemistry for this. It is completely general knowledge. Okay, you go home for vacation, and then you come back after 3 days. That means somebody else comes back after 1 day. Who stayed on the vacation longer? The one who came back in 1 day, or who came in 3 days? Huh? The guy who came back in 3 days had a longer vacation, so he stayed at home for a much shorter time, a much longer time. The person who came back in 1 day stayed at home for much shorter time. So the faster you come back, that means you stayed shorter time. Okay, so the lifetime of these excited states are going to be controlled by how fast it comes down. So when you go home for a vacation and then you come back after 1 day, that means you don't stay here too long. Another person comes after 10 days, that means he has a good time. He stays at home and then have good food and all this, so he has a longer time. Okay, so that is measured by these rate constants. This is radiative rate constants, radiation-less rate constants. This is the fluorescence. So if the fluorescence is very strong, that means this one is not going to be, molecule will not stay here too long. And then, so these numbers will tell you. So all these things you can keep track of this in a small picture like this, like a small, that one is called as Jablonski diagram. This is a guy who put together this picture. Okay. Okay. Any questions you have? Yeah.
You talked about shorter time and longer time. For this case, with short time, we can say fluorescence. If it's longer time, we can move to phosphorescence, right?
Okay. That is, I think we'll talk about those things a little bit later. So if something lives longer here, that means, if you go home and stay at home for 10 days, that means you can go around looking at other places, you can visit your friends and then eat at your grandmother's house, all kinds of stuff. If you come back in 1 day, you don't have a lot of time at home. You just stay home with your father and mother and come back. So the longer you stay, there are more options for you. So when a molecule lives longer in the excited state, it can go to the triplet, and then from there it can come down, and that is called as phosphorescence. Okay, so it depends upon the time scale. So the longer you stay at some place, there are more options for you. So I come here for 1 day, that means I will go tomorrow, and then I will probably go to the downtown and see something and go home. If I'm here for 10 days, then I can go and see terracotta warriors and all this stuff, and and do many things. Yeah.
One more question. Can one molecule get fluorescence and at the same time phosphorescence, or just fluorescence for one molecule?
No, the same molecule can do fluorescence and phosphorescence. Okay. So for example, if a molecule goes, you go home for 1 day for a vacation. So you are going to come back in 1 day. But at home, somebody has a car. That means you will go around and see places very quickly and come back. And you go home for 1 day, and then there is no car at home. There is no bicycle, there is no car. All you can do is walk around some place and come back. That means you cannot go to this place. It depends upon the rate constants. How fast is the rate constant from here to here? If it is faster, you don't need a longer time. If it is shorter, that means you need a longer time at home. So it is just a question of the time scale is very important. Okay, so this is one of these things, the Jablonski diagram. Okay, I will take 5 minutes break because I think we are going to talk about spin. It's a little bit more complicated, and you may need a little bit of a break. So now it is, what is this time? 10:50. Okay, so 11 o'clock will come, and 11:30 or 11:40 will stop. Then you can go for lunch, and then we'll. Okay, 11 o'clock, we'll come back. But you should try to read all this stuff. There is no point in myself talking. You have the PDF. Look through this. If you have, I think the book you can probably borrow from Dr. Leaping, and look through that. Okay. Otherwise, the whole thing is a waste. If I have traveled about, but I don't know how far away is Miami from here, and 18 hours flight. It's a pretty. I didn't like to sit in the seat and for 18 hours. I came here. I'm hoping some of you will learn some photochemistry out of this long trip I took, because I have a lot of things to do, but I just stopped everything just to come here to give some lectures. Okay, so you should try to spend some time, read all these, and if you have any questions, you can ask me when I'm here. Okay.